So, hi, welcome to our third Together C and C++ convention, or short TC CPPCon. I presume that you can hear me properly. If there's any kind of issue with my audio, with my quality, or if there's stuttering, then just let me know in Twitch chat. I am this week's host, Eisenwave, and I'll talk about C++ templates, what they are. I'll present to you various tips and idioms that you can use in order to step up your template game. Now, if you've never actually used templates before, that's also totally fine. This is a two-part presentation. So during the first part, I'll just introduce templates in general, why we need them, and go over function templates, class templates, and all these kinds of types of templates that are out there. And in the second part, I'll go into more advanced topics of variadic templates, modern language features that can assist you when working with templates, as well as constraining them. And finally, all of this will come together in the member detector idiom, where we will put all of all of the knowledge that we've gained to use, and where just all of these things kind of come together in one really cool idiom. Yeah, I'm from Germany, by the way, Zentrals, since you've been asking, but you probably wouldn't identify this as a German accent. So, yeah, hey. So, the first slide, I guess. Let's get started with this whole thing. I'll first throw a bit of a quote from the C++ standard at you. Don't worry, there's not going to be too much of this stuff, but I just think it's important to kind of use the terminology that you would find and the wording that you would find in the standard, but it's not going to get too troublesome. So, the C++ standard says that a template defines a family of classes, functions, or variables, an alias for a family of types, or a concept, right? So it's really about defining families of different things, of functions, of classes. But why do we need this in the first place? Might be an interesting question. So the idea here is that if you write code that only works with one constant, only works with one approach, only works with one type, you will end up repeating yourself at the end of the day. And by using templates, you can generalize this code, and you can make it much more powerful and much more concise also, since, well, you will have one version of it and not a million versions of it. So really, the goal here is generalize code using tools that are built straight into the language. But it is probably better to show instead of to tell. I think the font size on Godbold should be okay, right? It's a simple example. We have some kind of square function. The purpose of this is to take a parameter, which right now is just an int, to multiply that with itself, and to return the result. So this is a super basic function. Now the issue is, if we wanted to have this, let's say for floats, or for long ints, or for unsigned ints, then we would have to basically use another function, or we would have to just kind of copy and paste the entire thing. Right, so you can kind of generalize code by just copying and pasting it over and over. The issue is this quickly gets out of hand if you want to do this, I don't know, 5 times, 6 times, etc. This gets incredibly annoying, it's hard to maintain. So what we can do is we can use templates in order to generalize this function. So every function template, or at least before C++ 20, starts with this template head. So you have the template keyword with which you start a template, and then in either type name or class, in order to say that your parameter should be a type parameter, right? So in the parameter list of the template, you put all of the stuff that should be different between the functions that are in this family, as the standard described. So instead of just taking an int right here, what we do now is we replace this int with our type t, and this is now a function which takes some arbitrary type t, multiplies that with itself, and returns that result. And now, for instance, if we had a main function, what we could do is we could, let's say int x is square. We're going to specify that we want to square an int of, let's say 3, right? And maybe we return x, and you can see in the assembly output that the compiler just kind of turns this into a function that returns 9. So everything as intended. But, you know, obviously, since this is the template, it's now going to work with any type. So floats, you know, y is square of, well, let's say 3.f. And this is now also going to square 3, but it's going to work with a float. The idea is basically that we have to either provide these template arguments explicitly, or they can be deduced, in the case of function templates, from the argument. So here we provide a float argument, and because the float argument is t, this t right here can be deduced from the argument. But I'm jumping ahead a little bit, so let's just kind of return to in templates in general, because you don't absolutely have to use templates, and I think it's at least worth considering the alternatives. So what kind of other tools besides templates do you have to make things generic? So first of all, you have copy and paste. We've demonstrated with this, you just end up repeating yourself, it's hard to maintain, so you're really making yourself the tool. You can use something like code generation. This is also recommended by certain industry veterans, I guess. So for this, there is Cog, which is Python based and which just lets you run Python code inside of comments. And this would just output multiple versions of the same function, right? That's a little suboptimal. Then you have the C and C++ preprocessor, and this is just as text-based as well, code generation at the end of the day. Yeah, so with these you generally have zero type safety because it's literally just, it's completely text-based. It's possible to generate code that doesn't even compile, which is completely ill-formed. You have very poor tooling support because either it's put into some comment or it's put into a macro, and unless you use it, well, there's no way to really tell for the compiler what it's supposed to mean. And yeah, you have very poor language integration because it's easy to, you know, turn text into code, but it's difficult to turn code back into, you know, something that's useful for your preprocessor. And yeah, it's just worth considering these alternatives. Yeah, Easy as Pie has pointed out that we could kind of define a macro like this, you know, define square of x, which is going to do something like this, you know, just multiply x with itself. The issue with this is, first of all, you still need a bunch of pairs of brackets in order to make this work safely. So you will need at least 6 brackets or so for this to not suffer from multiple evaluations. And yeah, it's just a big mess. In C, this can never work safely. It's completely impossible in standard C to implement this correctly. And in standard C++, this is just, it's just a nuisance. It's going to look extremely ugly. But yeah, we can go further into that and why it doesn't work very nicely in the Q&A. Yeah, the timer on the top right is actually supposed to be a timer for the presentation, but I forgot to reset it. Now I can reset it right now, so that's going to give me a semi-accurate idea of how far we're into this. So function templates. Now we've already kind of presented one example with the square function. The standard basically says a function template defines an unbounded set of related functions. So this is pretty straightforward. An unbounded set of functions such as, you know, all the square functions with, you know, square of int and square of float, square, all these different square functions, you know, they're one big set. Yeah, no, it's not the Dracula color scheme. I don't actually remember which one it is. It's just one of the highlight.js schemes. This is an HTML presentation, by the way. I didn't know that C++ has different like semantics. Well, probably for the preprocessor. Yeah, I can go into the detail with that. Yeah, so the idea is really that you define function templates like this. Now you can only declare it, right? So basically just declare a prototype for this. It's also possible to just define it without any prototype, and this is what we've done before. And yeah, this is how you do it. Either you specify the argument for the template explicitly, or you use deduction so that this is done for you by the compiler. Well, if it's possible at least. What if t is not multipliable? Well, if you can't multiply t, that's kind of a big issue, right? Because, you know, it'll still let you kind of put in some type that can't be multiplied, like, I don't know, some arbitrary type. It'll still let you kind of put that into the templates, but then there's going to be, oh, well, not here. But there's going to be a compiler error in instantiation of the t-square where t is equal to foo. There's no match for operator, well, like for the multiplication operator. So that's what happens. You can still instantiate the template, but it might, you know, there might be some error in the middle of it. And this actually motivates constraining templates so that you can't make it, you can't instantiate it in the first place. So that'll be in the second part. Anyhow, type parameters, they can be, well, they're one type of template parameter, but you also have non-type template parameters. So you can use class and type name for the type parameters, and a lot of other stuff for non-type parameters. So you can have a template of int and bool and that sort of stuff. And those can be really useful in some instances. So for instance, here we have a simple add function. So this takes an int as a template parameter, which is called n. And all that this does is basically add this n onto the existing x that is passed in at runtime. And because the n in this case, it can't be deduced from anything in the function arguments, unfortunately, we will have to explicitly specify it when calling this. So that's one thing. However, here, for instance, we have another function template which accepts a size t, non-type template parameter, and this one is deduced from the array. Right, so when working with standard array, which is a very popular container from the standard library, you often run into the issue that you would want to write code that works with arrays of any size. Right, it's kind of unusual that you write code that only works with, I don't know, like a size of 10 or something. Right, and in this case, non-type template parameters can be useful because this way you can write a template that just covers all of them. And what this function does is it returns whether there are multiple elements in the array. So basically if n is greater than 1. And yeah, if we were to use this at some other point, then we would assert that this array of int and 5 in size would indeed have multiple elements. And for instance, if we add 1 onto 0, then this should indeed equal 1. So this is how we use non-type template parameters, or NTTP. In short. Sometimes what happens with templates is that you want to deviate from the norm a little bit. So for instance, there might be a special case, a special constant for which you can do things differently. Or for instance, what's also often the case is, let's say you have a type parameter, and if that type is bool, then maybe you can store that more compactly in a bit vector or something like that. Right, so sometimes you want to handle things differently for a particular type or for a particular constant. And if you look at the previous add function that we have defined, which just kind of adds n onto x, then you will notice that if n is exactly 0, we don't really have to do anything. We don't have to actually, you know, add n onto it. Nothing needs to be done. So this is kind of a special case. We could also just rely on the compiler optimizing an addition with 0 away for us. I mean, modern compilers can totally do that. This is just to illustrate the example a bit. So yeah, here we basically make use of this at the bottom, right? So add of 0 onto 0. This would be making use of this explicit specialization that we've provided. And we have also this this base template, this primary template, which is then going to be used for everything else. And yeah, so now I hope that you kind of have a bit of an understanding of how explicit specializations work, so we can dig into the quote from the standard and what it has to say about that. A function instantiated from a function template is called a function template specialization, right? So this add one function here, right? That is a specialization already. And so is an explicit specialization of a function template, right? So really this is still kind of belonging to the same template. We're just telling the compiler to do things differently if n is equal to 0, that we have some kind of special case. But yeah, it's just one more specialization. They're all specializations, but here we just kind of do things differently, as I've said. So there are some questions in chat. What would happen if we put int n into the empty brackets by explicit specialization? Well, like then this would be it would be ill-formed code. Yeah, it would just be a compiler error. So if we wanted, I mean, I can demonstrate this obviously on Compiler Explorer. So if we wanted to put int n in here, the compiler is probably gonna complain that, oh yeah, it's complaining about redefinition. Yeah, that's pretty straightforward of an error then. And also it's telling us in declaration of the primary template. Yeah, well, it's complaining that we're doing add of 0 in the primary template, so that's not allowed. Yeah, so another way to customize the behavior of your function templates is to use overloading. So sometimes it's not good enough if you have the same template or the same function template, but you just kind of add a special case to it. Sometimes you need a completely different one, right? So here we have a function, even, which just returns whether the parameter or whether the argument that we put into it is divisible by 2, right? And it's doing this using the famous trick using the modulus operator. So it's just checking if the remainder of the division by 2 is 0. Now, if we wanted to have an even function, which works for, let's say, something like a standard vector, right? And what it's supposed to do is it should return true when every single element inside of that is even, right? And we still want it to be called the same. Then we can do this. This is totally possible. So we can have multiple function templates that share a name, but that are still distinct templates. And so here we can see an overload for this, which accepts a const reference to a standard vector of some arbitrary type t right here. And this t is actually going to be deduced as well, so we don't have to explicitly specify it. And yeah, using the all-of algorithm from the standard library, it just kind of returns whether all the elements inside of the vector are going to be even. And we have a third overload that works only for int. And I want to explore this example on Godbolt a little bit. So let's just get the appropriate includes, which I haven't included in the slide itself. And yeah, that should compile. So let's say we call this, let's say we call one of these functions with something like a float or an int or something like that. The question is which one of these overloads is actually going to be chosen. Yeah, question clang gives a more informative error. Yeah, interesting. Now, overload resolution for templates, it's a bit of a complicated topic in general, and it definitely should be more reserved for an advanced presentation. But I just kind of want to explore it just a tiny bit. So let's say we have something like a standard vector of ints, and let's say we have 1 and 2, and we want to know whether all of the elements inside of this vector are indeed even. Now, theoretically, if everything went right, then this should just kind of return 0. In main. Oh boy, that's a lot of compiler output. Okay, so it looks like the compiler just kind of failed to inline all of this stuff, so we actually have to execute it in order to figure out what's going on. That's interesting. So yeah, the program returns 0. So this tells us that no, not all of the elements inside of this vector are even, unfortunately. But the question that I want to pose here is, how does the compiler actually know that it's supposed to call this function and not that function? And the way that this works is using overload resolution. So what the compiler, as a rule of thumb, what it does is it checks which one of these two functions is going to accept fewer types. That's probably the best way to describe it on a beginner level. So it'll basically see that if I have a vector that can basically work for both of these functions, but if I just have some arbitrary t, that it can be passed into this function, but not necessarily into this one, right? And overload resolution, as I've said, it's a bit of a complicated process, but if you know how to use it, if you basically know what you're doing just a little bit, you can really add a lot of functionality to your templates and make your life a lot easier. As for name mangling question from Twitch chat, well, I mean, there's always name mangling in the outputs, just it gets demangled by compiler explorer. Okay, so the next topic on the list would be class templates. So I think we've gone through enough material when it comes to function templates. So class templates are the second big type of templates. They've been there since C++ 98, since the very beginning. And what it basically is it defines the layouts and the operations for an unbounded set of related types. That's perhaps a bit of a complicated way to describe it in standard terminology. But yeah, the standard basically always says the same for all templates. They're all very similar. So, for function templates, it's an unbounded set of functions. Here, it's an unbounded set of related types. It basically always works the same no matter what kind of template we're working with. These class templates are incredibly useful when we want to define some kind of generic container or some kind of wrapper type that works with more than just a single type. So for instance, if you have some kind of, math vector class that you want to use to store a couple of floats or something, this, if you just do it for floats, you might have to rewrite all of your codes when you want to kind of switch over to doubles, or when you want to, pick precision. Do I want to use float? Do I want to use double? So class templates can solve this issue very elegantly. So here we have a vec3 class, and this is supposed to be essentially like a 3D math vector that just stores three coordinates, x, y, and z, of the same type. And we can not only define members, like data members, we can also define constructors, we can define member functions. So basically anything that you can do in a regular class, you can do just as well in a class template. So here, for instance, we have explicitly defaulted our copy constructor. And an interesting note here is that inside of the class, for your convenience, thanks to a feature called injected class names, you don't have to type vec3 of t. You can just type vec3, and this will basically use the t from here. Now, if we, for instance, wanted to type vec3 of t, that would be totally fine, right? We can still do that, but it's just optional, and your code is going to be a lot cleaner if you keep in mind that you can just kind of keep it away. You don't need to repeat yourself here. As for data members, like, it's pretty straightforward, right? We just kind of take the type parameter and we define a couple of members with the type. So this is fairly simple. When it gets into member functions, it gets a little bit less elegant, a little bit less simple. So let's say we have this a function template, a class template right here. So we have a class template called pair that accepts a type F for the first member and a type S for the second member. And this is very similar to how the standard pair class from the standard library works as well, except that it has a lot more features to it. So let's say we want to have a member function such as members equal, which just returns whether the first is equal to the second. And I'll just demonstrate how this kind of stuff works on Godbolt. Now, if we want to define this inside of the class, it's fairly straightforward, right? Super simple stuff. We just do it the way that we normally do it for any other regular class that isn't a template. If we wanted to define the same thing outside of the class, then we would have to repeat the template heads, basically the same thing we've used for the class itself. And now bool members equal const, because it's const qualified, and now return first is equal to second, but we still need to like qualify it with the with the name of the class itself. And that's how we can kind of define it outside. Now, right now, this is a redefinition, so we just get rid of this stuff. But you can tell this is a lot more code. And I just want to kind of demonstrate that the takeaway here is that if you define it inside of the class, it's usually easiest, it's usually most convenient for your member functions. If you define it outside of the class, I mean, like what, we've saved 2 lines in here and now we have 4 extra lines in here, and this just looks so messy because of this qualification, because of the redundant head. I mean, this is, yeah, it's just a little messy. And it gets especially messy when we have a template, like a member function template, inside of a template class. Because in that particular case, we actually need 2 separate template heads. So the upper one, this is going to be for the class template, and the lower one, this is going to be for the constructor. Now, perhaps you might ask yourself here, okay, like what is this constructor? What is this supposed to do? And the basic idea is if we have a pair of, let's say, a pair of int and float, then it might be in our interest to have this converted to a pair of int and int, right? Because, you know, an int and a float, like that's in principle convertible to, let's say, a pair of int and int, right? So this constructor could be useful. And actually, if you look inside of the definition of standard pair in the standard library, it does have this feature, right? And it has like 10 other constructors on top of that. It's crazy. But yeah, like maybe, you know, it's a useful feature to some. And so that's what this is supposed to be doing. And that's why it needs to also be a template, because it just accepts any other pair. Yeah, I hope you understand that example. So let's move on to specializing classes. Now, if you fully specialize a class, we've already seen how this works with function templates, right? It's basically the same principle. You also leave the template head empty and stuff, and you just kind of define a special case. Now, full specialization of classes, of class templates, is sometimes very useful. Because let's say we have this wrapper type here, right? So in this example, we have a wrapper that can store a t of any type. So it just kind of stores this t as a member called value, right? So if this was a wrapper of int, then it would store an int value. Or if it was a wrapper of float, it would store a float value. And we run into a problem when we have void as the template argument, because you can't store a member that is void. Now, perhaps I can just demonstrate this once again on Compiler Explorer. So let's say we have int main, and we want to define, let's say, a wrapper of int. We put one here. Let's call it w equals, I don't know. Well, we can't do equals, but we can just kind of initialize it with 5. And let's say return w.value. Right, so this is kind of a use case for this one. However, this is not going to compile if we use wrapper of void, because, yeah, lo and behold, it's not actually possible to have a void member. So now the compiler says, oh, you know, wrapper of t has an incomplete type, and the type is incomplete because we used void incorrectly, and so the compiler, just throws errors at us. Very unfortunate. But we can define a specialization for this, which handles this particular case. So now, a wrapper of just void can be left empty, and now we no longer have any kind of compiler error. Arguably, this wrapper is also not very useful right now, but hey, at least it compiles. Yeah, what if you passed const void? Well, I'm not actually sure. Can you? Yeah, I don't think that. Interesting question. Yeah, it looks like if we const qualify void, that is indeed not going to work very nicely. So a const void ends up being a const member of type void, and yeah, so the full specialization doesn't get triggered in this case. I haven't really asked myself what happens when you do a const void member. Okay, well, I guess, yeah, and I guess it's still a distinct type, and it's not going to work like this. So yeah, and Jakub Gamer is asking, can you omit the int in this example? You can, since C++ 17, because of class template argument deduction. So the fact that this is a wrapper of int is going to be deduced from, well, the way that we initialize this wrapper. So this is a fairly recent feature. It's not going to work in C++ 14, but it will work in C++ 17 and above. So yeah, here in C++ 14, we get missing template arguments before W. Perhaps I should make this a bit smaller so they can read more of it. But yeah, that's what happens. Yeah, no, and if we put const void in the specialization, that's not going to work. So these are distinct types, and I guess you would have to specialize for both void and const void. So let's move on. The specializations for classes are much more powerful than just full specializations. They are unique because you can have partial specializations. So essentially, yeah, you can have these special cases where only a portion of it is specialized, but not everything, right? And before we delve into the standard quote, before we dissect that one, let's once again investigate this example. So you have an array, and this is a class template which accepts a type parameter t and an arbitrary size t n. And all that this basically is kind of a wrapper for an array of size n and with type t. And this is awfully similar to how the standard array container works in the standard library, by the way. So this is by no means some kind of contrived example. That's really how it works in the standard library as well. Now there is a bit of a problem with this. Namely, if n is equal to 0, then we would end up with a zero-length array. And while some compilers allow that to happen, it's not standard C++. So according to standard C++, the program would be ill-formed, and this shouldn't compile, right? So we can partially specialize this though. So we can make this an array that accepts any type t here, but if the argument is 0, then we leave it completely empty. So it's not going to have a data member, it'll have absolutely nothing at all. And so then, for instance, if we have an array of int and 4, right, this is going to use this original primary template up here, but then an array of, let's say, floats and 0, this would be using our partial specialization. And yeah, like an array of int and 0, it's also going to use a partial specialization. Like an array of, like, I guess void and 0 would use it as well. So that's the idea. So this allows us to have stuff that has special cases, so to speak, but that is still generic in itself. So now that you have a bit of an idea of how this works, let's walk through the quotes from the C++ standard. A partial specialization of a class template provides an alternative definition of the template that is used instead of the primary definition when the arguments in a specialization match those given in the partial specialization. Right, so really what this means is that if let's say, you know, float in 0 matches the ones that we have provided here, then yeah, it's going to pick this one, this alternative definition, over the primary template. It's pretty straightforward. It's not so straightforward when you define, like, you know, 5 different partial specializations that all kind of have to work together and not conflict with each other. But yes, it's pretty straightforward if it is really this simple. So there's a question from chat. What about when you want specializations to share some behavior of the primary template? Well, if you want to share some level of behavior, for instance, you could inherit from a common base class. So that'll be a common solution to resolve that issue. But yeah, well, I don't see much of a better way than just inheriting from a common base class. Yeah, that's probably the best idea. And partial specializations, you know, they can be used for handling these kinds of special cases, but really they are a tool which is much more powerful than just this. So partial specializations are used in something that I would call type traits. And well, that's also how the standard library calls them. But it's really more of an idiom than like a specific language construct. So the idea is that we use all of these powers that partial specialization grants us in order to gain more information about a type, and maybe to like even get more template parameters out of it than we ever had before. So let's say, for instance, we want to, and let's go back to the original definition right here. So we have a struct array, right? And this contains a type parameter t, and it contains the size parameter n. Now, what if we had an array and we wanted to get the type parameter out of it? You know, for all sorts of metaprogramming purposes, perhaps we want to, you know, test, oh, is this going to be an int or something? Is this going to be an array of floats? Is this going to be an array that is longer than 5, right? So what if we want to gain this information from an array, right? And what we can do is we can define a primary template that just doesn't do anything at all. So this primary template, it's useless. It's not even defined. So if we ever try to like create an instance of this one, it would fail to compile. What's really useful is the partial specialization of it. So this partial specialization accepts a type name, t, so a type parameter, and it accepts a size parameter. And here in the parameter list for the partial specialization, it accepts an array of t and n. So what this basically means is that we specialize array info for the case that we are given some array, right? But we don't care necessarily what the type is. You know, it can be any type t, it can also be, you know, any size n, etc. And now, because we have basically deduced these, so what happens here really is you're putting in an array, you're deducing t from it, you're deducing n from it, and now you can work with these, right? You can do all sorts of stuff with this. So for instance, you could put this into a type alias, right? So this can be using value type equals t, or it can be type def t value type, depending on your code style. And we can also put a static constant into this array info struct, right? And so now basically, if we use some type, you know, let's say we have some array type 3 ints, right? It's like seemingly at first glance, it's not possible to kind of get the fact that it's an int out of this, or that it's 3 out of this. But when we use array info in here, so the array info of 3 ints would use this partial specialization, and out of this we can get the size, because the size is a static member, and we can assert that this is equal to 3, and this is going to work. And also we can test that the value type of this array is indeed going to be int, right? So here we can assert that the array info of 3 ints value type is the same type as int, and both of these assertions are going to pass. And yeah, that's basically how it works. So partial specializations are not just useful for handling some kind of special case, they're also useful for extracting information out of a type that, yeah, you didn't have before. And so they are an incredibly powerful tool, and yeah, it's definitely worth just kind of learning about it, because you can do so much with it. So I'll basically talk about variable templates and type alias templates in this context of this trait that we have defined before. So basically, this code surrounding type traits is often a little bit ugly, and using variable templates, we can prettify it, and we can also do that using type alias templates. Perhaps it's best if I just, now that this is spread over too many slides, I'll just kind of glue all of this together into one big code sample. So let's grab all of these different things, just put it all on Compiler Explorer, and yeah, also let's grab this stuff. Now we need an include in order to get standard size t, which is going to be C standard def. That's where it is. Okay, nice. It's complaining because we're in C++ 14 mode right now. There we go. No compiler warnings or errors. So really the basic idea is for variable templates that they describe a family of variables. And in this case, we're basically describing the family of all the array size _ v variables. And the purpose of this is just to make our code a little bit prettier when interacting with this array info struct right here. So previously, if we wanted to do this without a variable template, we would have to use array info of t and then kind of get the size out of this, with the namespace operator. That might be a little bit ugly, but we can make things a little bit more convenient by using this variable template. So for instance, with 3 ints, if we wanted to know, or I guess verify that the array size value of 3 ints is indeed equal to 3, we could do it like this, which is, well, considerably more elegant than if we did this without a variable template. So without the variable template, this would basically look like this. So it would look like this, which is a couple characters longer, a couple characters, less convenient. And the similar principle applies to type alias templates as well. So previously we would have had to use the array info of 3 ints, and then we would kind of need to use value type in order to get that out of it. But using a type alias template, we can prettify this code. So let's say we wanted to, verify standard is same v that, hold on, I need an include for that. Include type traits. So if I wanted to verify that standard is same v value type, right? I could do it like this. And yeah, that barely fits on the screen. It's a little bit longer than it needs to be. It's not terribly inconvenient, but you should note that if the type here, if array info t is dependent on t, which it is, then you also need type name in front of this to disambiguate on a side note. And you can save like 10 characters or something like that by using an alias template. So for instance, the compiler would not allow this to happen, at least not on C++ 17, I believe, without this. Yeah. So need type name before array info, because array info is a dependent scope, right? So type alias templates can also kind of help you, like get rid of one unnecessary type name keyword right here. And yeah, as if we wanted to do the same kind of thing using type alias templates, then it would basically look like this. No more value type. Oops, selected too much. That's how it would look. Which is slightly more concise, but like tremendously more concise when we when we deal with dependent types. Yeah, I mean, like, as for the stream cutting out, I've just experienced it as well. I've paused my own like view of the stream, and hopefully this is going to improve the quality slightly, since it's like less stress on my bandwidth. I'm not sure if I can maybe lower the bitrate a little bit. Hold on. Okay, so the bitrate has been set to 2000 now, right? From 2500. I hope this is going to improve the quality or like make it a bit more consistent. If there are any more issues, then please let me know. Yeah, so we're getting very close to the end of the introductory part right here. I mean, we've really gone over basically everything that I wanted to go over. We've discussed function templates, we've discussed class templates, specializations, partial specializations, type traits that you can sort of implement using partial specializations, and then how you can make everything just, you know, tie it up, make it a little bit prettier with variable templates and type alias templates. So that kind of concludes the first part, and we have time for a Q&A now. So if there are any questions that you have regarding templates or regarding the things that I've said in the presentation, now would be the perfect moment to ask away. Well, I don't understand variable templates. Are they just aliases for templates or what? Well, yeah, no, I mean, like, basically, the principle is that a template is always defining a family of something, as the C++ standard says. And this is not an alias, necessarily. This can be its own thing. Right, so this is basically a template for a variable. So, I mean, it's basically doing the same as just, let's say, inline const expr, hold on, standard size t, array size v of, you know, x or something like that, right? So this is basically just generating a variable like this for us using the compiler. But you know, it's just doing it in a templated way. Now, theoretically, and here it kind of gets into the super evil stuff that you can do with templates. You could make this extern, I think, as well. Yeah, this compiles, so you can make variable templates that are actually defined in some other source file and stuff like that. So they're really variables, but just with yeah, with a template head on top. That just kind of lets the compiler generate it for you. Okay, so Hala La Luyafail asks whether templates work with function pointers. Yeah, they totally do. So for instance, let's say we have our good old type name, I don't know, t square function. Let's get that thing back, right? And we return x times x. So with this, we can also create a function pointer that is going to be calling this one here, right? So for instance, we could define a pointer to some function, or well, give it a meaningful name, square pointer, that accepts an int, and we set that equal, we initialize that to int. right? And you can actually see in the compiler output that now we're storing a pointer to this square of int function right here. And what's also really cool about this is that the template parameter t right here, this is deduced from the type of the function pointer, right? So it's not like we have to specify, square of int or something like that. It just does everything for us. So yeah, templates, they work quite nicely with function pointers, and yeah, it's actually very nicely. So yeah, I alluded to the C++ preprocessor behaving differently than the C one, or did I misunderstand? No, I mean it's basically the same preprocessor, right? But to go back to this conundrum with square, right? So let's redefine this. X times x, right? And this is already somewhat safe because, if we put some operator in here, like let's say we say that we want square of 1 plus 1, then like it's not going to get messed up with precedence and stuff because we've already added a bunch of these. But there is a bit of a problem with this one, and that's basically multiple evaluations. So when we call this with some kind of function, then this function is just going to get copied and pasted on both sides, or I mean the function call, right? So so void foo, is just a function that does something, and well, okay, I mean we should probably make it an int so that it actually can be used in here. So now if we call square of foo, then what happens is you can see in the assembly output that we're calling foo 2 times, and that's really, really annoying. Because this now means that it's multiple evaluations, but it doesn't look like it, right? This looks like we're calling foo only a single time, but then surprise, surprise, it's being called multiple times. And these multiple evaluations are basically something that you can't really get rid of in C. Like in C, if you want to have a macro that works with any type, then it's just straight up impossible. There is no solution that is standard that you could use to fix this conundrum. Right? But in C++, what you can do is something really disgusting. Namely, we can define a lambda, right? So this lambda is just gonna accept, some auto x, and it's just going to then return x times x, right? And then we just immediately evaluate. Well, okay, I mean it shouldn't be x, obviously. It should be, let's say, y, because otherwise it gets substituted. And we call this with x, right? So this is how you solve the problem in C++. And now we have this call to foo. And you know what? For good measure, it's probably a good idea. Don't put a semicolon in here, and also put this entire thing into parentheses just for safety. But yeah, I mean this is ugly. This is like what? This is 1, 2, 3, 4 pair. No, 5. This is 5 pairs of brackets. Yeah, so this is pretty awful. And since C doesn't have lambdas, you can't really solve that issue in C. So that's the full story on why this works in C++ and doesn't work in C. And yeah, you can pass function pointers as template parameters. That's possible. That's absolutely possible. Is there any way we can restrict the types accepted by a template type parameter? So for example, restrict it to only double or something like that. Yeah, this is going to be part of the second part of the presentation. We absolutely can restrict them in this kind of way. So yeah, that's no issue at all. And we'll look at several possibilities for doing that. So yeah, like old school stuff would be Sphene. Yeah, you could, there are various tricks. You could also just put a static assert inside of it, but that's not really restricting it as much as it's just causing a compiler error at a sooner point. Yeah, you have concepts and constraints in C++ 20, which make this way easier than it has ever been. And yeah, we'll cover all of that in the second part of the presentation. Okay, so I need to I need to get a quick break, and then we will continue in a short bit.